Okay. Continue. Do you see my screen?
Yes.
Okay, so then first of all, thank you very much for the invitation, and also for me, pleasure to make my presentation for you. And you already heard my title of my talk. So then I'm from ID10 beamline of the ESRF Synchrotron. So I work at soft interface and coherent scattering beamline. In fact, this beamline on one sector has two end stations. One is dedicated for the coherent scattering experiments, probing the systems with coherent X-ray beam, and another one is made for the surfaces, major liquid surfaces in interfaces. And today I only will present my talk based on the part of the experiment done at the surface end station. And then a little reminder for people who is not working in this field that surface sensitivity with X-rays on different systems is gained by working at very small angles within few milliradians, and then to work before the total external reflection of X-rays from the surface. In this case, the propagation of the X-rays in the media is very small, and then like this we can separate scattering from the film or from the surface from the scattering on the bulk. Basically, bulk doesn't scatter because it is not reached by the X-rays. So this is what is important to understand for surface scattering, at least at the beginning. So then the short overview of the this end station activity. So for the surfaces, we apply like X-ray reflectivity to probe the structure normal to the surface of the film or interface. Then we use Grazing incidence, small angle and wide angle X-ray scattering. This is to probe two-dimensional organization on different length scales, atomic or nanoscopic, mesoscopic. So then Grazing diffraction is used for the crystalline systems. And also we are able to measure fluorescent signal from the interface to see elemental distribution near the interface. And all this technique can be applied for different types of the surfaces and interfaces like solid liquid, liquid or gas liquid. And in many cases, these techniques can be used simultaneously, that we obtain in one experiment at the same time different information on different length scales from the samples. And majority of the time, this beamline is used to study different type of soft condensed matter system. And one of them is like Langmuir films, which supposed to mimic a biological membrane. And then we can study the organization of this membrane, interaction with different systems like protein, DNA, or ions. And the other part is to observe the growth and the organization of nanoparticles near the interfaces, very often liquid-liquid interfaces. So then also to look on polymers, chemistry near the interfaces. And all this business is soft condensed matter. And I will show you today a few examples, which is kind of a challenge, because today I would say this is soft condensed matter for me, but it's more look like a hard condensed matter experiments, but you will see. And before going to the presentation, also I would like to give you some info about the ESRF in general, because last year we completed the upgrade of the machine, and we went to a new optical lattice. So now we increase dramatically the brilliance of the beamline and also the beam size. So this allows us to work with a smaller beam, brighter, and also to increase significantly coherence. For example, here, this dashed line, this is what we had before, and the continuous line, this is what we have now. Then you can see that brilliance increase several decades, more than 10 times, 20 times. And this give us a new possibility. And then, for example, here, just as soon as we had a beam, we made a comparison between the beam at the ID10, what we had before. We had a so-called high beta beam line where we had a small vertical beam size and relatively large horizontal one. And then this beam is focused with beryllium compound refractive lenses. And then with a new lattice, now at the same condition of the focusing, at the same distances. So you see that our beam becomes very small and pretty round. So then this allows us, so first this increased a lot the flux density on the sample. So we had a little increase in the intensity, like 10 times, but significant increase in the coherence. So measured at our beam line like 25 times. So this is to show you what seems would be a future of APS when the lattice will be also upgraded. And so today I'm going to present some results of two studies. One is CVD growth graphene in liquid on liquid metal catalyst, and another one is 2D super lattice self-assembly from lead selenide nanoparticles. So then I will try to squeeze these two different presentations in one and to link them with one idea. And then idea is following that both of them is two-dimensional material. And one of the known two-dimensional material, this is a graphene, which has two atoms in one unit cell. So this is a honeycomb structure of carbons with a thickness of one carbon layer, but also this structure can be built with for example, two types of atoms, and then this is known like hexanal boron nitride or molybdenum disulfide. And then what is the interest to these systems that due to the, so this is a property of these two-dimensional materials. So at first, these layers are very stable. They are strong mechanically and thermally. So then they have a very high electron mobility in these sheets. So then basically massless transport and extremely low spin orbital interaction. And due to that, there are several possible applications for this, like new field effect transistors, flexible electronics, biosensors, solar cells, nanofiltration, like porous, and also lightweight, ultra high strength material. And before using this for industrial applications or other scientific applications, we need to know how to grow these materials, two-dimensional sheets of graphene, for example, in a large area, defect-free and fast. This is what is interest for the industrial applications. So, and before this, if we look how usually the graphene or other two-dimensional materials are grown, so then first we take a solid catalyst as a substrate, we prepare this, then with the CVD technique, we grow a film, multi-domain film on this surface. Then this is going on at a high temperature. So then we cool down, we put another, we add a carrier film, which is usually a polymer, which is spin coated, for example, on the surface. Then we put this to the acid to etch the catalyst metal. So then it is transported to the target substrate, some devices. Then we again do chemical processing to remove the polymer film, and then we have our graphene on the targeted substrate on the device. So then here you can see there are several drawbacks. First, this is many steps. This is time consuming. So the quality is reasonably, it's low of this 2D because the, due to the defects of the solid catalyst, the 2D material grown also heritates the defects on the, from the substrate. And also we have some contamination due to the metal catalyst or due to the process, which is going on afterwards. And additionally to these things, so this process is environmentally non-friendly because we use acids. And also there is a lot of consumption of the catalysts, which we cannot reuse. So we need again to process it to go back to the crystals, because usually this is used a single crystal for that. And we have a chemical waste. And then looking at that, So it might be an idea that, for example, if we take, instead of solid catalyst, we take a liquid catalyst, copper. So then here, advantages following that. First, the surface is more isotropic. So then it is homogeneous, smooth due to the high surface tension of liquid metals. So then we can hope to grow much better crystals without defects. So then, due to the high diffusion on the surface of the atoms, we can anneal defects, or they can simply go away from the samples. And another interesting thing is that the viscous force on liquid is much slower than the friction on solid of the 2D material. So then there is a possibility, might be, to remove more easy the samples from the surface and make, for example, like a continuous production of 2D materials. So then it will be fast, single domain, low energy consumption, and the reuse of the catalyst, and minimize the chemical waste. So then this was our idea when we organized the consortium between IDT beamline with 5 other institutions. So in Greece, Germany, also in France, CA, then in Netherlands, university, and the LPM company, which helped us to build a reactor. So then we made a project with the name of LMCat, liquid metal catalyst, for synthesis of 2-dimensional materials. We obtained the grant from European grant from Horizon 2020, and we start our work. And first, we built a LMCat reactor for the CVD growth. So then here, this reactor, this is a part where we have a furnace. We melt the copper, and then there is a chamber where we can grow our sample and then make simultaneous characterization of the growth and the post-growth sample with X-rays, because this is a X-ray transparent beryllium windows, so then we can do surface scattering techniques. And then on this lid, on the top, this is an optical microscope and the Raman microscope to characterize growth and the property of the grown flakes. And everything is going on in situ at a very high temperature, so above the temperature, melting temperature of copper, and also at the atmospheric pressure. So then a few words about our process. So then to process this, we have major content of the gas is argon, and which is at 1 bar atmosphere, at 1 bar pressure. Then we have a little concentration below 5% of methane, and also we have some amount of hydrogen to control the growth and etch the surfaces. So then when methane reach the hot copper surface, it decomposes, and then carbon stick to the surface, and then it has enough time to stay on the surface, migrate, and then meet another carbon and start to grow. What is also interesting to use copper is that the solubility of carbon in copper is very low. So that's why practically all material stays at the interface. So then another annoying thing could be that copper has a very good evaporation, and then we have a lot of copper around. And to suppress evaporation of copper, we work at the argon, which is heavy gas, and also we work at 1 bar. So that's why we need X-rays with high energy to penetrate also through this dense material to characterize what is going on during the growth. So then here on this image, oops, wait a second, I need to remove a pointer. So here you can see a short video that this reactor is installed on the ID10 beamline. So then we install it close, then we start up our gas system, and then we start growth and measurements. And here, this bright spot, copper color, this is a melt of copper, which we see through the optical window. And at the same time, oops, when we look further, then we can see in real time how graphene flakes, they nucleate and start to grow. And you see there is interesting things that they grow like hexagonal flakes, But then when we have enough density of these flakes, they start to interact with each other. So then they organize also honeycomb structure where the surfaces of these flakes are aligned. And at the end of the growth, we see that they don't like to stitch together. And then what we think that this is due to the repulsive interaction on a short length scale, because they interact on a far distance to align themselves through the capillary interaction, because it is a long range interaction. But then when they go closer, as these flakes are charged, so they start to repel. And then in our interest is to find the process, okay, we can also do this, to be able to stitch these aligned crystals together atomically and then to produce a large area graphene flakes. So here you see the scale that this is 0.2 millimeters bar, and this is only one type of the growth where crystals are reasonably small, but we can grow one single flake of graphene more than 2 millimeters on this. And you see that all this process, what you saw on the screen, is happening within 3 minutes. And on this microscope, what we see, this is a radiation difference between the copper, which is black in this case, and the graphene, which is more white. And this is really one atomic layer of graphene on copper, what we see here. So then we can characterize by even without X-rays, with the optics, we can characterize the speed of the growth, the shape depending on different condition of the growth, and with the Raman to see the internal defects in the graphene. So then with X-rays, which questions we can address? For example, how many layers we grow on the top? Okay, we know that this is one layer, but with X-rays we can confirm this. So then what is the roughness of the graphene layer? What is the lattice parameters? So then what is the size of the crystalline domains? So then first type of the experiment is X-ray diffraction, what we perform, and then what we can learn from that. So then if this is in real space we have crystals, but in the reciprocal space, this small in one direction objects transform to the crystal truncation rods. And then from the size of these rods, we can see what is the size of the crystals, and from position of these rods, we can see what is the crystalline structure. But you already saw that these graphene flakes, they float on the surface. And then we can only see sometimes the reflection from these crystals when they're passing through the Bragg scattering. And then if we put a detector on expected position of the Bragg, so then we can see from time to time these reflections. Other approach to study the structure of these crystals is to grow the surface completely with the flakes when they don't move, and then afterwards to rotate the whole bus of copper under the beam and put them in the reflection. So then in this graph, you can see what is we can observe as a grazing diffraction, and then this is a representation of the reciprocal lattice of the graphene, so this hexagonal structure. And here we see the 3 families of the Bragg peaks of graphene. And what is interesting first to notice here, that these Bragg rods along the QZ direction, which is normal to the liquid surface, are very narrow, and they also don't spread up. And this measurements was done at 22 keV at 2 milliradian grazing angle at the temperature of liquid copper. And in one set of measurements, we was able to observe 700 rods from our graphene flakes. And then from these rods, we are able to calculate the position of these peaks and the lattice parameters of the graphene. And then here, the error bar for the Q vector and also the lattice parameters of the graphene and the carbon-carbon distance are calculated from, this is a statistical error from this 700 rods. then this is quite good accuracy. And also what is interesting, if we compare this value, for example, the lattice parameter, what we see here, with the lattice parameter of the graphite, you see that they're very close. So then it can guide us to an idea that there is some peculiarity in the thermal expansion of the graphene layer, that at a high temperature of a molten copper, we have the lattice parameters similar to the graphite at a room temperature. So then the next question is what I told you, that if we look how the width of the Bragg rod depends on the QZ, so this is a representation of what we did. So then we can see what is the bending of the film. For example, here in the Nature paper from the group of Novoselov and Game, so they made the electron microscopy measurements of a free suspended graphene flake, and then they saw that the Bragg rods, they expand. So then due to the bending of the flakes, and in our case that they are almost constant, what we see. So then we can say that on the liquid copper, graphene flakes are extremely flat, so that we basically cannot see this bending on our scale of measurements. And the next step, what we did also to characterize grown graphene, we applied the X-ray reflectivity measurements. So here, to remind you that we change the grazing angle and we look exit angle equal to the incident angle, and then by ratio between the incident beam intensity and the scattered intensity, we can deduce, so this reflectivity afterwards from the curve, we can deduce the structure normal to the surface. And then the one thing what I didn't told before, but which is very important for the X-ray reflectivity measurements, that if so our copper sitting on the tungsten support, and then if we do nothing, so the copper doesn't like to wet tungsten, and then if we melt it, it just make a ball, and it's very difficult to measure reflectivity on a ball. And we made a modification of the tungsten surface. We made it rough in a way that effective wetting angle would be much smaller, and then we can cover the surface with a small lens with a with a more higher curvature, which already allow us to do measurements. And for example, here, if we look how what we can see on two-dimensional detector when we reflect from the flat surface. So this is here, this is rest of the direct beam. This is specular reflected beam. So they are well separated, and this is a point like scattered beam. But if we put on the curved surface, we see that instead of one, let's say, point, we have a line. And then even for reasonably flat surface of copper, it is curved, but we need to understand or find a way how to analyze reflectivity data from the curved surface and get valuable information. So then we developed a technique how to analyze this data to be able to reconstruct reflectivity data like it would be measured on a flat surface. So then if we have a curved surface, which is a part of the spherical radius, and then we have a beam, it's scattered on the surface, so it will spread in some angular fan. And then you can see that a little piece of the beam, which we can select here, will scatter somewhere on the detector. So then if we will find a technique how to identify on a given pixel which part of the incident beam reflects from the surface, so then we can normalize it, and then we can know what is the intensity which corresponds to this Q, because each ray now is reflected for a different Q vector. So then we succeed to make this mathematics and to be able to calculate in both directions, so simulate data and go back from the experimental data. So here you can see that this is a reconstructed 2D image from series of measured data. So here this is specular reflection which is spread on the 2D detector at one incident angle if the surface would be flat. So then here this is a grazing angle for the effectively flat surface, which is in our case the top of this circle. So then, and this is pixels on the detector. So we can have such kind of a shape of our reflected signals where each pixel corresponds to a different QZ, so the scattering vectors. And then from the shape of this curve, we can find what is a radius, curvature radius of our sample, which is important for the analysis. And then afterwards, we can find the value to normalize this data on the incident beam. And then we can go in from to put all these normalized pixels intensity in one curve, and then we can reconstruct the curve like measured from the ideal flat surface. So here, the experimental data on the top of the ideal flat surface, so that's why we don't see. But on this insert, you can see that this curve is built from many points which are from different pixels on the detector. They are not equidistant because they are randomly distributed, okay, due to the curvature of the surface. So then we succeed to make the analytical process how to analyze such data, and then we apply this to our measurements. And then idea was to see that if this is our reflectivity and this is type of the model, like we have a liquid copper and the graphene layer. So then depending on the distance between the graphene and the copper, we can see that the change in the reflectivity curve, that minimum stochastic oscillations will also move depending on the distance between graphene and the copper. So then if we have several layers, we'll have another type of the reflectivity curves. And so then if we have a surface which is rough due to the capillary waves, so then again, curve looks different. And then if the graphene also follow or don't follow the curvature of the liquid copper, so also again, the curve may look differently. And then this gives us the idea that the data which we will obtain is possible to use to reconstruct this information. And then this image shows the final result of our measurements and analysis at the red curve. This is a reflectivity curve on the liquid copper. And the blue one is the reflectivity curve on the copper with graphene. And then from minimum, we was able to find, so what is the gap between the graphene and the copper. In this case, gap we call the distance between center of the graphene layer and the deflection point on the copper surface. And the graphene was modeled like a Gaussian-like shape of the carbon atom. And then we fix the electron density in the graphene layer. So we also fix the thickness, and then fitting parameters was roughness of the graphene, roughness of the copper, and the gap between them. So then knowing this gap, it is possible to calculate what is the interaction force between the copper and the graphene, and then to apply this for the separation process, which I showed you from beginning. And so here, this is a quick summary of this part of the presentation. So that we found the lattice parameters of the graphene on liquid copper in situ. So then we could see that the graphene sheets are not bent. We was able to see that the roughness of the graphene and the copper is very low, and it is consistent with the roughness of the capillary waves, which produced by the liquid copper. So then the graphene gap between graphene and the copper, and the crystal size from the Bragg reflections is kind of not smaller than 0.6 microns, but optically they are quite bigger. And this is also, we confirm that this is single layer graphene. And as a continuation of this work, which is not shown with another slide, so we got a new project now, a European project to develop a method how to take these graphene flakes from the liquid copper. So to more go to industrial applications like make a continuous production of graphene. So then I'm going to next part of my presentation about nanoparticles. So then I show that we can use the two-dimensional systems. Materials are useful for different industrial and electronic applications, but the type of the 2D construction of atoms is limited by the periodic table of elements, and so then there are some limits. But if we want to get a new type of materials, so then idea is to use artificial atom of nanocrystals, where each atom, so in this case, this nanocrystal could be a single crystal with different facets, which is also part of the modification, because the type of the facets can influence on the interaction between these nanocrystals, and then the size and the composition can, for example, here you know that depending on the size, they can emit the light with different wavelengths, which can be used for optoelectronics or the application of this type of materials. And then having this in the base, we decided to see how these nanoparticles on the liquid surface, they grow and organize two-dimensional arrays attached, so two-dimensional materials. So then the process is, from one side, quite easy. So we take lead selenide nanocrystals with low polydispersity. The average size depends on the different samples between 4 and 7 nanometers diameter. So this is a truncation cubes shape, and then they are stabilized in oleic acid and dissolved in the toluene. So then as a carrier of substrate, we have ethylene glycol, which is liquid. So then we put toluene on ethylene glycol. Toluene is light, as it is on the top. So then toluene evaporate, and with time, the lead selenide nanocrystals, they condensate on the surface of ethylene glycol, and then they will create different structures. So then at the different stages of this process, we can pick up the sample on, for example, electron microscopy grid, and then see what is going on at a different type of time of growth. But what we see that during the time, the lattice parameters are changed because it be constrained. So at the beginning, we have, for example, like a very rare random patches. Then it creates like hexagonal structure. Then it changes to more close to like a cubic, and then here is a cubic. And also we see that on the TM diffraction that of this, that there are different Bragg peaks, Bragg reflection from the system. That some of them appear, some disappears, which can tell us that also these particles, they have different orientation. But going with this method, first of all, we see already transferred sample. Then we don't know, maybe it is damaged due to this transfer, and also by scooping the samples at different time, we may miss some intermediate structures. So that's why we decided to go to measure this with X-rays in situ during the growth, and then so we built a cell where we can drop our liquid with nanoparticles on ethylene glycol, and then simultaneously measure during evaporation G-SAX signal to see organization of nanoparticles between themselves, and then or with the wax to see what is the orientation of these particles to following to the internal structure of the particles. So then this is experimental setup. This is a cell. This is a bus, which afterwards has nanoparticles, which is dropped so with a syringe going through this hole, and then two detectors, one measure SAX and another one measure wax. And then this is what we have. So here will be left, it will be wax, G-wax signal, and the right picture will be G-SAX signal. So then when the toluene didn't evaporate too much, and then we have a diluted nanoparticles, and then basically what we see with the SAX signal, we see the small angle scattering from individual particles. So then this is a form factor of the nanocrystals. While on GID, so here it's difficult to see, but point lines, this is to guide where we should see the scattering from internal crystalline structure of nanoparticles. So at the beginning, we don't see any scattering. So then time bypass, and then after roughly at half an hour of operation comes, we see that this image transformed to another one where there are several Bragg peaks which correspond to the hexagonal packing of the nanocrystals. And still not many information from GVAX. We don't see sharp peaks, we just see something broad scattering around expected position. So then time goes on, and then you see that the hexagonal structure is changed. So now it is kind of deformed, and some little intensity appears on the expected VAX signal with the Bragg. And then at the end of the process, we have already new lattice, which is similar like this one, but if we make analysis, so this is already cubic lattice, and then you see that clearly Bragg peaks appeared. But this is not a ring, so this is kind of small stretched arcs. So it means that there is a very clear Bragg peaks from internal structure of the nanoparticles, and they are very well oriented. So they don't have a random orientation. So they are very well oriented in one type of direction for the faces. And after experiment, we also take the samples for characterization. So now, from this image, you can see that if we would have the nanoparticles on the surface oriented randomly, all type of orientation, we would have circles. But if, for example, one face, like for these crystals, 100 face is oriented upwards, so then we should see the Bragg peaks. And then this also present how we calculate where to put a detector to follow the process. So then this is already experimental results. So we see some expected Bragg peaks, and then for different type of the nanoparticle size and at the end of the growth, so you see there is a arcs which tell us about the orientation of the crystals on the surface. And then if we look, okay, what we can get also from this image, we can take some position, but from this width of this position of the peak tell us, on SACS, tell us what is a change in the lattice organization of nanoparticles, and from the width of the peaks on the VAX, we can say about the also the coherent length of these crystals. So then this curve represent what is the lattice distance for between nanoparticles, nanocrystals with the time. And we see that with time that the lattice parameters change, that at the beginning we have nanocrystal distance like 9 nanometers, but with time the distance changed and becomes much shorter. So then there is a contraction in the cell, but also the change of the type of the cell. And then we have almost 17% decrease in the particle-particle distance. And if we look on the nanoparticle diameter, so this is 5.7 nanometers, but the distance between, at the final stage, the distance between nanoparticles is 7.6 almost. So then the distance is 34% is bigger than the size of the nanoparticles. But anyway, the particles, they are well oriented and they scatter like a single crystal. So it means that the atomic planes between neighboring nanoparticles, they are coherently aligned on atomic scale to be able to scatter like a single crystal. So then why it is happened? And then we saw that it could be the idea that there is a necking, so that the shape of the particles remodels, and some atoms, they go in between these nanoparticles to make the solid interaction and align them atomically. So then if we look on the VAX information, so then by taking the width of the Bragg peak, for example, this one, and we see how it changed with the time. You see it becomes narrow and narrow. So then it means that really nanoparticles, they align, and then they grow a new superlattice, which is a crystal made of nanocrystals. And so from this width, we can say that at least there are several nanoparticles going to this process, and then they organize a new supercrystal. So also the mosaicity change from the width. And when we take this sample after the growth and we put on the high angle annular dark field scanning microscopy, so then we can reconstruct the 3D image of our grown system, and you see that it's really this confirmed that there is a necking between, so there is atoms between the nanocrystals which make a necking link between them, and then this makes this two-dimensional arrangement very solid, so that when we take it out from the surface, it's really like a solid sheet that it doesn't break. So you can take it and then it's ready to dematerial for some other application. Also, we made the X-Ray reflectivity from this system to see what is the thickness of the layer. And then what is interesting to notice that the blue line, this is experimental data, and the red line, this is the best fit if we fit with the model that we have a spherical nanoparticle coated with some surfactant, a shell, and then we try to fit this by changing the distance between center of nanoparticles and the interface, and also the density of the particles near the surface. And so then whatever we do, we cannot get better than this one. So then we realize that this model doesn't work because we really need to take into account that our particle is not spherical. It is, it has a facets shape. So this is truncated cube. And then when we take into account that our nanoparticles, they have a shape, and also they are well oriented in one direction, all of them, and then we add some surfactant layer around shape and the density and also necking between them. So then we was able to fit nicely our model to the experimental data. And all these measurements also some of our colleagues, they made a Monte Carlo simulation and then tried to understand what is the phase diagram of the interaction. And then it was a model quite simple that we take the facet which is interact between the neighbor nanoparticles, and we put attractive patch which is has a certain percentage of this area. So the larger this patch, the more stronger interaction. The smaller patch, the less stronger interaction. And then when this attractive patch is big, so then the particles, they attract to each other rapidly, so that at a kind of a random manner. And then it makes disordered structure, which looks like a hexagonal. But when the attractive patch is much smaller, so then there is a time and also the thermal fluctuation, which helps to arrange them in an ordered manner and then to create from this truncated cube to create a square lattice. And then this was, algorithm was able to draw this type of the phase diagram, where here this is a ratio between attractive patch and the size of the facets. And then here this is interaction energy in sense of kBTs, so that thermal energy. And then it is, so we see that we really can go through the liquid type of arrangement, so the hexagonal packing to the square packing. So then, okay, this is not our path exactly, but it looks like anyway, during our experiment, we went from this phase to this one phase and then to this one, so that we never went directly like that. And then this slide would summarize our understanding of this process. So then at the beginning, so this is first top graph, this is a top view, and the low graph is a side view on the interface. So then when we put initially the liquid with nanoparticles, so then they're quite dilute, so then they do not organize between themselves, and then only what we can see the smaller scattering from individual particles. So then, upon increase of the concentration of the particles on the surface, so they start to feel each other and interact at the gas-liquid interface. But at the same time, the particles have a full degrees of freedom to rotate near the interface. So then when they rotate, so effectively they look like not faceted or truncated cubes, but more like spheres. So that is why when this number of nanoparticles increase, but still with a full rotation degrees of freedom, so then they pack in a hexagonal manner, because it is like a close packing of balls. But this is not hard balls, soft balls, but they are packing in hexagonal structure. And then when we increase concentration further, we start to see that hexagonal packing is destroyed, because now the particles, they start to feel that they are not spherical, they are cubes. So then this helps to freeze rotational degrees of freedom a little bit, and then they go from hexagonal to first distorted cubic or square lattice. And at the end of the process, so then they organize all in the same manner, well oriented with 100 plane, in this case upwards, and then they create a necking. But what should be added here and was not told before, because as you probably remember at the beginning, that these nanoparticles in toluene, they was stabilized with oleic acid. And then what drives to go system from this hexagonal orientation to the cubic one? This is a fact that this stabilizer, oleic acid, is not covalently bonded to the particles. This is just a kind of a soft shell around. And then this oleic acid can, and this is what it happens, it dissolves in the ethylene glycol slowly, and then due to this very slow process of dissolving, they removed one by one, and this gives a time for nanoparticles to make well orientation between themselves. And then afterwards, when all the oleic acid goes away, they can go close face to face, stitch, and then afterwards to create this necking process. And so then here, this is my time is over, and then I would like to thank you for your attention, and also the numerous collaborators for these projects. So, thank you very much.